All right, so in order to talk about what it might look like to build a safety case, I want to just quickly think about like what the development cycle for a new idea or a new system might look like. So a lot of times you come up with an idea, and then you put in some amount of effort to go about like designing this idea that you just came up with, and then you go and you deploy it in the real world. But given kind of the topic of this workshop, you're all probably realizing that there's something missing here, which is that typically before we go and deploy our system in the real world, we want to actually do some amount of validation to ensure that the system is going to do the things that we actually designed it to do when we go and deploy it, so that we can have confidence when we deploy it in the world and that there won't be any like unintended consequences. And you can imagine that this is extremely important for a safety critical system. So for example, in aviation or with aircraft, because if we deploy our system in the world and we haven't done validation on it and there's these unexpected failure events, those failures can be quite catastrophic, resulting in loss of property or even human life. And so for this reason, it's really important to kind of put in this extra effort to validate our system before we deploy it. And now in this workshop, we're talking about AI in these types of scenarios. So now this just gets even more complex because we're talking about, maybe deploying these vision-based systems that use neural networks to do various tasks. So here's 2 case studies I used in my research during my Ph.D. On the left, we have a camera that's mounted on an aircraft that's taking images of the surrounding sky. And we pass those images through some sort of machine learning model in order to estimate where there's other aircraft in the sky so we can avoid colliding with them. And on the right, we have this taxi navigation scenario where we have a camera that's mounted on an aircraft and it's taking images of the runway, and we're using those images to be able to navigate. So these are both very safety critical scenarios, and it's really important that we can understand the failure modes or potential failure modes before we deploy the system so that we know that it will operate safely. And so because this problem was already quite complex, validation in general, and now we're adding this extra complexity of AI components, validation becomes even more important to the point where you might even spend, especially for these extremely safety critical scenarios, you might even spend more time validating your system than you did designing it in the first place. So you might be asking, okay, well, how do I go about doing that? No worries, got you covered. So actually, I have spent a lot of my postdoc working on a new textbook called Algorithms for Validation, and we discussed lots of different algorithms for doing this, some of which I'll kind of preview today. It's actually the 3rd book in a series of algorithms books that my advisor has been involved with. The first 2 are more on the design side of things, so algorithms for optimization and algorithms for decision making. And so in those books, we like design systems, optimize them, and then once we're done, we come over to this book and we say, let's check if what we designed actually does what we intended it to do. And so we actually just submitted the book last week. So we have a contract already, and there's also already a full preprint available online for free of all 3 of these books. So you can check it out, algorithmsbook.com if you're interested. Okay, so that's kind of how all of this fits together. And just in case that somehow didn't resonate with you, or you're like from Gen Z and you understand everything in memes, here's another way to put it. So the first couple books, this is where you could laugh if you wanted to. In the first couple books, we mess around a little bit. And then we come over to this book and we find out what the things we created actually do. But ideally, we want to find out in a controlled and safe environment, such as a simulation, instead of in the real world once we've deployed our system. Unlike these people. The one on the right is actually me. I was still an undergrad. I hadn't done any validation yet. I didn't know this. All right. So those are some fun systems. But in general, we're interested, at least in this book and in this talk, we're interested in decision-making systems, and specifically decision-making systems that operate over time. So that could be anything like a robot, a self-driving car, autonomous aircraft, financial system, healthcare system. All of these are very safety critical systems that tend to make decisions in sequence. And in the framework that we introduced, we kind of just wrap all of these things. They've already been designed, and we just call them the system, basically. And then the other kind of component of validation is saying, okay, what do we want this system to do? And so we typically formally wrap that or formally specify that into a specification. And then these 2 things can go into a validation algorithm, which outputs some sort of information about whether the system may or may not satisfy the specification. So that information could be something like a failure analysis. It could be like a formal guarantee. So can we prove that a system under some set of assumptions will satisfy specification, an explanation of the behavior of the system, all the way to when we deploy the system at runtime, can we have runtime assurances on the system? And the way that I kind of see all of these things fitting together, I think the Swiss cheese model is a really good model of this. If you've never seen it before, I'll explain it really quick. Basically, the idea is that all of these different categories of techniques have various limitations or kind of like holes in them, just like the slices of Swiss cheese. But you can imagine if you like stack enough slices of Swiss cheese together, you won't be able to see through to like what's beneath. And so the idea is like these holes don't line up in these various methods. And so if we stack enough of them together or do enough of them, then hopefully nothing can get through. Okay, and so I know it's kind of like late in the day and like maybe you're ready to tune me out. If you are, this is the one thing I hope you take away from this talk. There's really just no silver bullet in safety validation. So when we go to think about making a safety case for like an AI system, we can't just like pick one of these and say, okay, let's just apply this one and then let's go deploy our system. But really like all of these methods have different limitations and we're gonna need to apply a whole bunch of different techniques to sort of build a safety case. Okay, hopefully you don't tune me out, but hopefully you take that one away. So for the rest of the talk, I'm just kind of going to go very high level into each of these different categories of techniques. And I'll talk about some different techniques that we talk about in the book and that also our lab has developed, but just going to scratch the surface to give you an idea of like what's possible and what these techniques look like. But you should definitely check out the book and lots of other interesting research if you're interested. Okay, but for now, we'll start with failure analysis. So with failure analysis, there's kind of like three main tasks that we tend to think about. The first task is just falsification. So that's basically just taking our system and saying, can we find any failures of our system? We just want to know like a few different scenarios where it might fail. Then we can actually take that one step even further and say we actually want to sample from the distribution over failures for a system. So this is more difficult because we now have to have like a probabilistic model of our system. And then we also have to be able to then kind of like enumerate all of the failure modes that our system might have. But it's also a lot more informative because now we have this distribution over the full set of failures for a system. And then we might want to take that one step even further, which again becomes increasingly more difficult, but also more informative, where we would actually want to estimate the failure probability of a system. And this can be really useful, especially like when working with FAA, for example, because we want to be able to understand the probability of failure so we can make decisions about whether or not the system is safe enough to deploy. Okay, and so there's lots of different techniques for doing all of these things, but they're all kind of motivated by the same story. So let me tell you that story real quick. So essentially, we have this plot here of a system. It's an inverted pendulum for those of you who care, but you don't really need to think about what it's doing too much, other than just knowing that red is bad, and any red trajectory you see is like a failure where the pendulum fell over, essentially. So one way you could think about doing all of this failure analysis is just like simulate your system a whole bunch of times. So basically just do like a Monte Carlo analysis where you just simulate a whole bunch of times. You get some successful trajectories, you get some failure trajectories, and then we can look at the failure trajectories and we can be like, okay, this is like what some of the failures look like. It can fall over to the left, it can fall over to the right. This is roughly what the distribution over failures looks like. And then we could also get a nice like Monte Carlo estimate of our probability of failure by just like dividing the number of failures we saw by the number of simulations that we did. And this all works fine if you have a system like this. But the general problem that we run into, especially in aviation, is that there's kind of an issue as failures become more rare. Because when failures become more rare, which is very common in aviation systems, which is of course a good thing, it becomes much more difficult though to do all of this failure analysis, because if we just simulate our system a whole bunch of times and look at the failures, if failures are rare enough, we might not even find any unless we simulate our system for like months on it. And so in general, like we need to basically, for these systems with rare failure events, develop more efficient algorithms to do the failure analysis for the system. So to summarize here, like these direct sampling Monte Carlo methods are generally pretty inefficient for systems with rare failure events. They might not find any failures at all. But luckily, there's lots of research out there on failure analysis for systems with these rare failure events. So I've just listed a few techniques there, many of which we talk about in the book, so you can check them out. But yeah, basically the general idea is that we just want to do something that's more efficient and like more targeted than just this direct sampling approach to actually deal with systems with rare failures. So I'll just give you a flavor of what a couple of those look like. So here's one interesting one, doing the task of falsification. So to explain what's going on here, we have this aircraft taxi system where we're taking images of the runway from a camera that's mounted on the aircraft. We downsample those images, and then we feed them into the neural network, but we actually feed a perturbed version of those images into the neural network, assuming that there was like some noise in the image or something like that. And the question we want to answer is like, is there a sequence of these noisy images that could actually cause the aircraft to veer off the runway? And so it turns out if you just like simulate the system a whole bunch of times with like random perturbations, random noise perturbations, you won't really find any scenarios where the aircraft goes off the runway. But that doesn't mean that there's no scenario where it could go off the runway. And in fact, if we do this more targeted optimization to actually find a scenario where the aircraft goes off the runway, we're able to discover one of these trajectories. And specifically what we're doing here is something called Monte Carlo tree search, where we basically, this is kind of the search tree that Monte Carlo tree search built out, and it's searching through these image perturbations in sequence to try to find a sequence of them, which would actually lead the aircraft to leave the runway. And so the idea that you can take away here is just that basically instead of doing this direct sampling approach, we can apply more targeted techniques like optimization or planning methods to actually find sequences that cause the system to fail. Okay, here's another example of a system on an F-16 where we're investigating the ground collision avoidance system. So basically, if the aircraft is like in a nosedive, we want the system to pull the aircraft out of the nosedive to avoid colliding with the ground. And so you can see here that it fails in this case. A failure would be like if it hits the ground. But it turns out for this problem, failures are quite rare, which is of course good. But it's also a very high dimensional problem. So we can have like various disturbances on the roll, pitch, yaw. We can also have disturbances on the angular rates. And we're looking at these disturbances applied in sequence over time. So once you kind of add all of that up, the problem ends up being like 1200 dimensional. So this is like a very high dimensional distribution that we're trying to sample from. And the goal in this work, which was done by one of my lab mates, Harrison, was to actually try to sample from the full distribution over failures, even with this like very high dimensional space. And so the way that they did this was using something called B.S.A.S, which is a technique they created that relies on diffusion models to be able to model this very complex high dimensional distribution. So the thing to look at here is like, this is the ground truth failure distribution that came from running Monte Carlo simulations for many, many compute hours. Often this is like intractable to find in the first place. And then if you look, there's some other methods that they tried out, but you want to basically compare what's in the red to the red over here. And if you look, squint hard enough, you'll notice the red here matches much more closely to the distribution that we see for the true failure distribution. So again, key takeaway is like by using some of these more advanced modeling techniques, we're able to overcome the fact that these failures are very rare and that we have this high dimensional search problem and actually sample from full distribution. Okay, so that's failure analysis. So that was like finding failures of a system. The next thing that we might want to do is say, okay, given a set of assumptions, could we actually prove the absence of failures for a system? And so that's kind of this idea of formal guarantees. Okay, so just to give a really simple illustration of what a formal guarantee might look like, we could do something like reachability, where we say we have this like 2D state space here. We're just gonna be like, okay, we start in one of the states that's inside of this purple box. And we have this really simple dynamics function that's just like our state at the next time step, our x position is 2 units greater than our current one, and our y position is 1 unit greater. So just really quickly in your head, you can think about what happens to this purple square as we apply these dynamics. And probably you thought of something like this, where you just took this square and you said, okay, well, every single point in here is going to go over 2 to the right and up 1, and then you get this new square. So that's a simple, really simple thing. We know exactly what states can be reached next. And if you say we had some set of dangerous states up here, we could guarantee that we would never reach them. So that's kind of what formal methods typically look like. But with math, that tends to be more complicated. So for example, maybe instead of like dynamics that were just these two linear equations, we actually have a neural network or something like that. They're still equations, they're still just big mathematical formulas. That's really all neural networks are. But it's not so easy. We can't just do that in our head to figure out like what happens to this square if I put it through this equation. But with some fancy math and a bunch of extra tricks, we actually can do this. And the way we describe this is a field called neural network verification. There's lots of really cool, really interesting research here. And if you're interested in learning more, our lab has a survey paper on this, and I also made a cool introductory YouTube video on it that you can check out. I'll provide these links at the end again as well. Okay, so that's all super great. We can actually get these like guarantees on the output of our network. But some of you are probably thinking right now, like, well, yeah, that's cool, but like formal methods don't scale. And so kind of sounds like what's coming next is I'm going to convince you that that's not the case, but I kind of agree with you. Scaling formal methods is actually pretty hard. In fact, I'm actually going to give you another reason beyond the reason that you're probably thinking about for why they don't scale. Oops, wrong way. Okay, so to do that, I want to put this question in your mind. Why can't we just like formally verify the behavior of an LLM? So maybe there's like one-off things where people have tried to do this or something, but I think in general, it's not controversial to say that we like can't formally verify the behavior of an LLM. And I think a lot of you are probably thinking, well, it's way too big. So we have LLMs, are large language models, they're huge networks. And so we would just need verification tools that can scale up to these like giant networks. And yes, I think that's true. We don't have verification tools that can scale up to the crazy amount of parameters that these networks have. But I think there's also one more problem that a lot of people don't think about as much, which is we need a way to actually specify what properties we want to verify. So like these formal guarantees, they often verify input-output properties. What is the input-output property? And not only do we need to be able to just like say what it is, but we need to be able to write it down mathematically for our verification tools to use. And I think it's just not so obvious how to do that. So to kind of elaborate on that a little bit, we'll go back to this taxi problem where we're trying to steer the aircraft safely down the runway. And then let's consider a few different versions here. Let's consider a state-based controller for the system. So it's taking in the true state of the aircraft and controlling it down the runway. Let's consider an image-based controller. So it's now taking in an image of the true state. And then finally, somewhat unrelated example, let's consider what it would look like to actually verify an LLM. I don't know if you can read this, but by the way, I made this initial graphic when I was prepping for my PhD thesis defense, and I think you could tell what was on my mind. The prompt is, will I pass my thesis defense, if you can't read. Okay, so I want to now go through and kind of fill in what this table would look like if we wanted to formally verify all of these properties. So starting with the top row, we're going to look at like what is the inputs that we want to verify on, and then what is the set of desired outputs we want to make sure that we achieve. So first, we'll just talk about what they look like in plain English. So for example, for the state-based controller, the possible inputs, so we're inputting the state and using it to, in this case, estimate our position on the runway so we can navigate. And so the input here is just states on the runway, and the output then is also states on the runway. For this image-based controller, the input is all images of runways. And the output is, again, states on the runway because we're estimating our location. For an LLM, the input is all possible user prompts. And then in general, we want LLMs to output harmless language. Okay, so that's in plain English. But now let's go through and like try to mathematically say what all of this is. So if we look at the state-based controller, possible input states on the runway, actually pretty easy to define. We can say like we have some cross-track position, like how far we can be from the center line. We have some heading. And actually like the set of possible values for this is just like a rectangle. So we can actually describe this mathematically. Same with the output. Okay, all possible runway images. I don't really know how to write that down mathematically. That's pretty challenging, I would say. Output, we're still good to go. We know it's like states on the runway. Okay, LLM, all possible user prompts. I don't know how to write that down mathematically. Harmless language, definitely don't know how to write that one down mathematically. So there's some challenges here that we still need to fix. For my PhD, I did try to tackle one of these, which was this image-based challenge where we don't know how to write down like the full set of images that look like a runway. Because again, like we could input any image to our controller, but we really only care about it working for like the subset of images, which is the set that looks like the runway. And that's pretty difficult to write down. So one thing that we worked on in this work was to try to use a generative adversarial network, or you can really use any generative model you want to try to capture the set of plausible images that looks like a runway. So we were able to actually apply this to this taxi problem and get like formal guarantees with respect to that set of images captured by the generative model. So I won't really go into too much detail explaining these, but we can kind of get like guarantees of which states are reachable over time and when the aircraft might move. Okay, so going back to this table, I think this still needs a little bit of scaling here, and I think there's still this one remaining challenge, which is just like, okay, let's say we can somehow scale these formal methods up to these large networks. I don't even know what it is that we're going to try to verify with them. So I think these are really interesting problems to think about if you're looking for new research topics. Okay, so yeah, that's kind of the general question. All right, that's formal guarantees. All right, I'm going to go through the last two actually pretty quickly. So explanations. So far, we've kind of been like, it works, it doesn't work. I don't care, we just know that it can work. But we do actually a lot of times want to know why it works, because if there's things we missed during validation, if it's working for the wrong reasons, then we can't expect it to generalize in the real world. So there's a chapter in the book about like these various types of explanations we can generate. So for example, we could like take an image from this taxi problem and like check what the network is focusing on. And it should ideally be focusing on regions of the image that are actually important for the task. So there's lots of different things you can do here. I also think that this field of like mechanistic interpretability for these larger models is super promising, and I'm really excited to see where that goes along these lines as well. Okay, so that's all I'm going to say about explanations. Last example is runtime monitoring, which I think is super, super important. And the reason why is because we actually like do our best when we do all this offline validation. We've done our formal methods, we made some assumptions, we did our like failure analysis, we also made assumptions. What if those assumptions were wrong? And also they probably will be wrong because the world is very complicated and it's pretty difficult to like capture everything that goes on in the world. Here's just a couple of examples. This is like a Waymo vehicle approaching just this giant stream of water coming out of the road. Not a thing that's easy to think about when you're like coming up with all of your validation scenarios. And then I think Marco actually showed this video as well and perfectly motivated it because he actually showed a solution of how to do runtime monitoring if you come across a scenario like this. But this was a case where like a truck was transporting traffic lights. If I had to guess, Tesla did not have truck transporting traffic lights in their validation cases, if I had to guess. And it's really hard to account for all of these things. Here's like an example in the aircraft taxi case where like on the left, everything's working fine. And then on the right, we come to a point where like another runway crosses over the runway that we're currently on. We didn't account for that during training, and so it just totally veers off. To be fair, this was like a research system. I think that like if you were designing the system in real life, you probably would have thought of this. But the point is just that there's lots of things that like we'll never be able to think of it. And so that brings up this fair point that I think I get one of these questions, at least one of these questions, every single time I give a talk like this, where people say, well, how can I capture all possible scenarios that my like crazy complex system is ever going to end up in? Like, I don't even know what they are. So how am I going to do validation? You just kind of like throw up your hands. And my response to that is like, yeah, I would say it's definitely a problem that concerns me quite a bit. But I think that there's some hope here, which is doing runtime monitoring. So it's like we're inevitably going to miss stuff when we do offline validation. We have all of these assumptions that we've made, and so we need to be monitoring at runtime when we're potentially violating those assumptions. And then ideally, we can flag scenarios that might be dangerous before they actually cause this danger. And you could do something like enter safe mode, or if you have like a remote operator, you could transfer control back to the remote operator, something like that. So I think this is extremely critical. And there's lots of interesting research out there, which is some of which has already been talked about today. So I would just emphasize that. Okay, so let's just wrap everything up. Again, the takeaway I want you to have is just that there's no silver bullet here. We should really be applying techniques from all of those different categories of techniques. in order to build a safety case for these extremely safe systems. Okay, and so I'll wrap up. There's a link to lots more links. So there's a link to the textbook there. I also taught a class with all of these techniques in the winter quarter, and all of the lectures are publicly available online. So if you want more jokes and more fun slides, you can check them out. And yeah, I'll wrap up there. Thanks.